knowingly or unknowingly, as a child or as a teenager, this particular substance called light has been fascinating each and every human species on this planet. Right from ancient Greek philosophers like Aristotle, Socrates, to our modern philosophers like Einstein and Newton. So let us do our part by igniting that child within us and try to understand the nature of light. The first thing that comes to our brain when we talk about light is that it helps us to see objects. In this particular case, a sunlight is hitting the pen and the light is being reflected by the pen towards our eyes. This is how we see a pen. For example, let me take a glass ball. The light is hitting the glass ball and therefore I am able to see this particular glass ball. If the light is gone, there is no glass ball. If the light is there, there is this glass ball. This is how we see objects. Secondly, light helps us in the process of photosynthesis. Lastly, light helps us in increasing the syllabus of the students. Although light helps us in many ways, yet the question still remains, what is the true identity of light? Is it a wave like the ripples in the water? Or is it a particle that has a fixed position and a momentum? What is light? This particular question, whether light is a wave or a particle, has been haunting physicists since centuries. Some tried to define light as a particle, whereas some tried to define light as a wave. But if we look closely, if we look very closely, in the case of the waves and the particle, these are two different identities. These are two different things that cannot be merged, because in order to define waves you need different set of rules. In order to define a particle you need different set of rules. In case of waves, the first thing that comes to your brain is not localized. Okay? In the case of particle, the first thing that will come to your brain is they are localized. Okay, you can take, suppose this is a particle for me. I can point at it and say, look, it is there. In the case of waves, I can't do the same thing. I can't say, look, there is the wave. No, all I can say is, it's all over there. So, second thing about a wave is, they interfere. They interfere with one another. In the case of particle, they bounce off. So, in order to define waves or particles, you need different set of mathematical tools. You need different set of thinking or approach. The first answer to this particular question was given by Sir Isaac Newton, where he defined light as tiny atoms-like particles. And this particular theory was known as corpuscular theory of light, with the help of which he was able to explain the phenomena of refraction. A refraction is a phenomena in which light, when it travels from one medium to another, it bends. In this particular case, this is the separation between the two medium. The first medium is air and the second medium is water. For me, the light is going from air to water, and this is the normal. So, when a light goes from one medium to another medium, it bends. So this was what Newton tried to explain in his theory of refraction. Although Newton was very much successful with his corpuscular theory of light, where he explained light as a particle, yet there was one thing that he could not explain in the phenomena of refraction, it was the change in the speed of light while traveling from one medium to another medium. Also, if we think light to be a particle, then a simple picture would be, if I have two beams of light, something like this, and if it is a particle, then it should travel somewhat like this. All the dotted points out here is the particles. When they meet each other, they'll collide. One will bounce at a certain angle, one will get reflected by 180 degree, or some by 90 degree, okay, or some will go through. Yes, the picture has to be something like this, according to the particle nature of light. They should not interfere, they should bounce off, the expectation. Whereas the reality is something like this, the two beams of light crossing each other, interfering. So there were faults in the particle nature of light given by Newton. While Newton was working with his particle theory of light, where he was trying to explain the phenomena of refraction, there was a Dutch physicist who was working with a wave theory of light, because there were faults in the particle theory of light given by Newton. For example, the diffraction, the bending of the light when it passes through a certain barrier. There was this Dutch physicist known as Huygens, and the theory given by him is known as Huygens' theory of light, where he lays down a principle that says every point on the wavefront, is the source of secondary wavelets that spreads out in the forward direction and propagates at the speed of light. This was what Huygens said in his wave theory, with the help of which he was successfully able to explain the phenomena of refraction, reflection, also diffraction. So let us see these three phenomena. One with particle, how is it going to look like with a particle? How is it going to look like when we consider a wave? And we'll see that what it is with the wave that explains the diffraction pattern in a precise way that a particle nature of light cannot do. Before starting with the particle and the wave theory regarding the refraction, reflection and diffraction, let us see how many types of wavefronts are there, and what are wavelets and what are wavefronts. There are three types of wavefronts: plane wavefront, spherical wavefront, cylindrical wavefront. These are the main wavefronts. So in the case of plane wavefront, this is my old wavefront. Okay, this particular line is my old plane wavefront. And when I consider every point, okay, according to the Huygens principle, every point in the wavefront is a source of secondary wavelets. So every point in this wavefront, okay, every point in this wavefront is going to produce a wavelet. This is my wavelet. So every point in the wavefront is a source of secondary wavelets, and it propagates in the forward direction and travels with the speed of light. So in this case, this is my old wavefront. This is my secondary wavelets. This is my secondary wavelets. And what this wavelet is going to do, since every point is going to create a wavelet, okay, secondary wavelet, so I can draw a line, something like this, a tangential line with all this. Then this is my new wavefront. Okay, in the same way, again this is going to produce wavelets. Okay, every point in this wavefront is going to produce wavelets, secondary wavelets, and then I can draw a tangential line, and that is going to be my new wavefront. And that in that particular way, this is going to go further ahead, moving forward with the speed of light. This was what Huygens was trying to explain in his wave theory, okay, when he considered light as a wave. So this is how it is going to look like in the case of reflection and refraction. The incident particle is coming, that is the incident beam of light, when we are considering it to be a particle. So let me say it as incident particle. So when the incident particle is coming, it is hitting the plane mirror. This is my plane mirror, and then getting reflected back at a certain angle. Okay, and then when I consider the case of a wave, the incident wave is coming, it is hitting the plane mirror and getting reflected back. A little satisfactory regarding both the cases. And then, case of refraction, the incident particle, it is coming, and since this is a medium, this is air and B, this is a glass, okay, it is coming, it is hitting the surface and it is bending, okay, it is bending towards the normal. Then at the exit point, it is again bending away from the normal and going, the original path of the particle should have been something like this, whereas the path has been changed due to this particular medium, and now the original path is this. This is in the case of particle. And when we consider a wave, the incident wave is coming, at the surface the wave is bending, okay, towards the normal, and then at the exit point it is again bending away from the normal. So this should have been the original path of the wave, whereas it has been changed due to this medium, and now this is the original path. So in both the cases of reflection and refraction, somehow the picture is a little okay and a little satisfactory as well. In the case of diffraction, let us look into the picture of light as a particle and as a wave. In the case of particle, this is the light bulb. The moment it glows, since I am considering the particle nature of light, therefore particle has to come out, okay, and particle, it has to go in a straight line, because one of the properties of the particle is that it travels in a straight line unless something is obstructing its path. Okay, so as this glows, then I have particle, okay, traveling. I have this barrier, okay, I have this barrier in the path of the light rays, where this barrier is going to block some amount of light, and when it blocks some amount of light, that is the particle, okay, then this particular part where I have kept the barrier should be dark. Simple logic. If I have light rays coming like this, and this is my barrier, I have light rays coming like this is my barrier, then this part should be dark, because light is a particle and it should travel in a straight line. Therefore this part should be dark, but in reality it is not. We have some amount of light even at this particular region. Okay, it is going to be somewhat like this, not like this. It is not going to be, straight. Only this part is going to be light up. Okay, it's like I am going to light up only this part, whereas I am going to keep everyone in darkness on this particular part. No, it is going to be somewhat like this. Okay. In the case of waves, waves bend. Yes. So when I light up this bulb, then it is going to emit some waves. Okay, it is going to emit some waves, and then I have this barrier. That this particular picture, when I consider it to be a particle, it should have been like this. This should have been dark. Whereas when I consider a wave, it bends. Hence, I have this particular part also light up. This is the point where the particle nature of light fails and the wave nature of light succeeds. Then after Huygens, there is this famous scientist whose name was Thomas Young. He does one famous experiment, and it is said that this is the particular experiment that lays down the foundation of modern physics. The name of that experiment was Young's double slit experiment. And this experiment also confirms that light is a wave. It creates interference pattern. Okay. So what he did in his experiment was he used a coherent source of light. A coherent source of light is those type of sources, okay, those type of light beams that has no phase difference, or the phase difference is the same, and it is monochromatic. The frequency is also the same. So, in simple word, in order to perform this experiment at home, at your own place, you need a source of light that has the same frequency and the phase difference is also the same. Okay, and the beam has to be monochromatic. So, when he took a coherent source of light and he took one slit first, okay, he made only one opening so that when we drop any kind of stone in the water, then ripples are formed. So it is something like this. Okay. Then he made two openings in his slit. Okay, this distance is very, very small. Then he made two openings on his slit, and then what he observed is, since the ripples in the water is going to progress in this way, yes, so when it was observed in the screen, okay, when he allowed photons of the same frequency to pass through these two slits, they formed something known as the interference pattern. An interference pattern is something like this. At this particular point, okay, this boxes that you see out here, not particularly a box, okay, this is going to form a bright fringe. This particular part is going to be bright. This particular part is going to be dark. Again, bright, dark, bright, dark. Okay, this was what he observed in his particular experiment. That he got a bright fringe, a dark fringe, bright fringe, a dark fringe, something like that. It is like the two waves are interfering with each other and hence giving you this particular pattern. In order to understand the bright and the dark fringe phenomena obtained by Thomas Young, you need to understand what is constructive interference and what is destructive interference. So, in order to understand this too, you need to understand something about the waves. This particular part is known as amplitude. The topmost point, okay, in the positive axis, the topmost point is known as crest. And the lowermost point here at the negative axis is known as trough. Okay, and this is the direction of travel of the wave. Plus, one more thing you need to understand is, if I take this particular point from here to here, okay, this particular length of the wave is known as wavelength. Suppose if I cut this particular part and join this part out here, then it completes one cycle. This is my wavelength. So, in the case of constructive interference, this is my wave 1, okay, this is my wave 2. Here you can see that this particular part and this particular part of both the crest are meeting each other, and they are not out of phase. They are not something like this. They are something like this. Hence, when I get the result, they should add up. Right? They should not cancel each other. They should add up. Therefore, the amplitude should increase. Okay, so in this case they are in phase, in phase, in phase. Hence the result that I get from 1 plus 2 is with more amplitude, and the point of the crest is higher and the throg is lower. So this is the case where I get the bright fringes, the constructive interference. In the case of destructive interference, I have wave 1, I have wave 2. In this particular part, I see that my wave 1 is on the negative side, okay, and my wave 2 is on the positive side. Something like this. They are out of phase. So when I do 1 plus 2, the result is going to be nothing. And in this particular part, my wave 1 is on the positive side. My wave 2 is on the negative side. So when I add up 1 plus 2 in this particular case, it is going to be again nothing. So the result in the case of destructive interference is dark. There is nothing. This is what Thomas Young got from his double slit experiment. A bright fringe, a dark fringe, where a bright fringe symbolizes a constructive interference. A dark fringe symbolizes a destructive interference, which clearly showed that light is a wave, not a particle, because a particle is going to bounce off. It is not going to interfere, whereas waves will interfere, forming patterns like this, a bright, a dark, okay, where a bright, in case of bright fringe, we have the constructive interference where they merge, okay. In the case of dark fringe, they will not merge, in fact they will cancel out each other, okay. So this particular experiment done by Thomas Young made us very much sure that yes, light is a wave. Diffraction. It is somewhat similar to your interference and supports the wave theory of light. A diffraction is the bending of waves when it encounters any kind of obstacle. In this particular case, I have the incoming light waves, okay, and this is my aperture. So in this case and in this case, you can see there is one difference, that is the opening of this aperture. In this case it is big, in this case it is small, okay. So in case of diffraction, it depends on the opening of the aperture also, okay. It is because, for example, let us take the example of sound waves. Consider this to be room 1 and this to be room 2, okay. In both the cases of the sound wave and the light wave, I have a speaker in room 1 that is playing some kind of music and producing sound waves. One fellow sitting at room 1 can hear the music at any corner of the room, and I have this small opening for room 2, okay. In room 2, a fellow is sitting out here, can hear the music, though the intensity could be a little low as compared to room 1, but he can still hear what kind of music is being played at room 1. It is because sound is also a wave and it spreads, okay. So in the case of light wave, I am blowing some bulb in room 1, okay, and hence the light waves are coming. I have the small opening, the size of this opening and the size of this opening are the same. So in the case of room 2, okay, the light is being lighted up in room 1. In the case of the light waves in room 2, in case of sound waves, it was spreading all over like this. But in the case of room 2, okay, in the case of light waves in room 2, we do not have the light waves spreading everywhere like this, okay. We have this region got lighted up, okay, not the entire region. It is because the wavelength of the sound waves are very high whereas the wavelength of the light wave is low. And it depends on this aperture, okay, the opening of the aperture, whether the wave, the incoming wave, is going to spread entirely or at some regions. As the light waves undergoes diffraction, it forms a pattern somewhat like this. This particular region is known as central maxima. Okay, and this particular point, this region, is very much brighter than compared to the other bright spot. Okay, it is somewhat similar to your interference, where we have the dark fringe, bright fringe, dark fringe. But in this particular case, the difference is this particular spot is very much brighter as compared to the rest. Okay, and out here you see that the aperture is small. Okay, the meaning of this, the increasing or the decreasing of the size of the aperture, is that we are trying to match with the wavelength of the light. Okay, we are trying to match the wavelength of the light with the opening of the aperture. Okay, so in this particular case, we have decreased the size of the aperture, hence we can see that the central maxima has increased. Okay, again the pattern is the same. We have this particular spot to be brighter than the rest. The rest is bright spot, bright, dark. This is how diffraction confirms that yes, light is a wave, not a particle. After Huygens, Thomas Young, and experiments like interference, diffraction, polarization, there is this one more fellow, a genius mind known as James Clerk Maxwell, where he states that light is a propagating wave of electric and magnetic fields, which means that light comprises of electric field and magnetic field oscillating perpendicular to each other and perpendicular to the direction of propagation of the wave. He says that light is an electromagnetic wave. He reveals another picture of light and states that yes, it is a wave and it is a electromagnetic wave. Thus, this particular statement, also interference, diffraction, polarization, Huygens, Thomas Young, everyone confirms that yes, light is a wave, not a particle.